Hey guys, how's it going? I hope everybody is enjoying the end of their semester and working hard. So today we're going to be doing Chapter 11, and we are also going to be first going over what is in store for the rest of the class, which is not much. So let's go to Blackboard first, and let's go to the announcements. And just to recap everything, so our Exam 3, I will have it graded soon within the week, or within the next couple of days actually, as well as the Practice Exam 3. And they were due last night. Well, today is Monday night, and they were due on Sunday night, the 10th. The final exam will be accessible starting this morning. So right now I'm doing this lecture on 5/11. So the morning of 5/11, Monday, it was available. And you will have until 5/22. So if you look at the calendar on the bottom right here, that is next Friday. Not this Friday, the 15th, but next Friday, the 22nd. I need to have all of your grades in, including your lab grades and everything calculated by the 24th, the latest. So I want to get it done realistically on the 23rd. So that gives you guys time to ask how you're doing or ask what grades you have if you're wondering, or check your lab grade to see if there's anything wrong or missing that you think is odd. So definitely feel free to contact me. Some of you already did, to ask how your grade is. I got a lot of emails today, so I will respond to them after this lecture, or probably tomorrow, because I'm pretty tired. All right, Chapter 11 I'm doing right now. Additional lecture, so it's going to be a Chapter 12 through 16, like, highlight topic lecture. And that'll be, I'll put that within the week. That's just to prepare you guys for CHE-122. The practice final exam will be due on next Sunday, the 17th, so a week before the final exam is due, just to give me more time to grade it. And also, it is a practice, it's a homework assignment, so I'll only give you a week to do it. I think that's fair. Now, lab grades, I have not received them yet. I'll let you know when I do, and then I'll post the grades on Blackboard in a separate column, even though you probably might see that your other professor did that on your lab Blackboard, but I'm going to do that as well, just so you see if the grades are different, grades are the same. If you have any questions about the grades, please reach out to me, because I am putting the letter grades in your CUNY first, so I have control. I have not dropped your lowest test grade yet, and that will be done after I grade the third exam. And I'm assuming most of you guys did very well, just like the second exam, I hope, right? So the dropping the exam will probably be, for some of you, maybe the first exam, because we took that during class. So yeah, we'll see. Just let me know if you have any questions or you want to see how you're doing. Okay, so Chapter 11, we're going to cover acids and bases. So we have a basic idea of acids and bases. Get it? Basic idea? That was terrible. All right. We have this idea that of dissociation, right? Because I talked about it when I went over electrolytes, right? Remember, the strong electrolyte dissociates 100% of the molecules, such as HCl. I'll write down some strong electrolytes with my pen. Let's see, pen. Right, so, all right, strong electrolytes. And we talked about all this ionic salts, but more importantly, we talked about strong acids / bases. Now, this is where we're going to cover a lot today. And also, in weak electrolytes, or weak E, we talked about weak acids and bases. So all of this means is that for strong acids and bases, they are strong electrolytes, meaning they are going to go through 100% dissociation when they're added to an aqueous solution, meaning added to water. And for weak electrolytes or weak acids and bases, they only dissociate a very small percentage of the time. And I explained that in Chapter 9, I think, when we went over solutions. So you can go back to that and see more of that. Okay, so we can skip this stuff. There's blood samples, you need to know about pH, stuff like that. But let's talk about the definition of acids and bases. Now, there are several definitions. There's this thing called an Arrhenius acid, a Bronsted-Lowry acid, right? And they all mean the same thing. We're going to be covering these different definitions that are different, basically, thoughts and thought processes and ways of rationing out what an acid does in terms of behavior, or what a base does in terms of behavior when it's added to a solution by these scientists, Arrhenius, Bronsted, and Lowry. So Arrhenius acid, a way that he thought it was is that it's a compound or a molecule that produces hydrogen ions, H+, when they dissolve in water. Okay? So you see this equation, dissociation of HCl with water, right? You put it in water. That's what this means. The H2O above the yield sign, that means it's put into water. It's reacted with water. And it dissociates completely into H plus and Cl minus. This is very similar to what we saw for our decomposition reactions, our dissociations of our electrolytes. That's exactly what we see. And here we go, are also electrolytes. We know that. So this is basically what they do. Another way of describing acids, which I think is more helpful for you guys going forward, and just a quick, good thing to remember, is acids have H plus, or they have H, whatever, H plus, and they want to lose H plus. So acids, so the idea is everything wants to be neutral. Nothing wants to be acidic, wants to be basic, meaning stability-wise, being neutral is better. That's why ionic bonds and covalent bonds are so strong, because you have a positive, even if it's covalent, you have partially positive bound to partially negative. Those neutralize each other, and they like that, and that's a very stable bond. But with things like acids, when they're reacted with water, you have a lot of charges working around, and it's just like, it creates a bad environment. And at that point, HCl doesn't want to be, the Cl doesn't want to hold on to H, and the H will dissociate. So it has this hydrogen, and it loses it. Now, so something of characteristic of acids is, I just wrote that, is they have the hydrogen and they want to lose it. So the hydrogen equals acidity. The more hydrogens you have, not the more acidic you are, because there are compounds that have 3 hydrogens and aren't very acidic, such as phosphoric acid, for example. But generally, if you have hydrogen, you're going to be more acidic than if you didn't have hydrogen, because that hydrogen is able to, in all these cases, what we call deprotonate. What that means is, so let's break down that term. It's another term. I know I'm going all over the place, but deprotonate. Okay, proton is probably the root word that you all recognize. A proton, think about what a proton is. It is just a positive charge. Think about what a hydrogen atom is. Hydrogen atom has a proton. It has no electrons. It has no neutrons, and it has 1 electron. An H plus, that means you're removing a negative charge, right? Because you're removing an electron. You can't get rid of the proton, or else it's not hydrogen. Get rid of the electron, and what do you have? The hydrogen atom in a +1 charge is just a proton. So if you didn't understand that, you can rewind. But that means in a positively charged hydrogen is the same exact thing as just a proton. So that's why we can use those terms interchangeably. Proton and hydrogen ion. So hydrogen ion, this is the same thing as a proton. Not, they're very similar. They're exactly the same thing. And we can use these terms interchangeably. So when we say we want to deprotonate something, that means we want to D, meaning take off, or subtract, deprotonate. So take off a H plus. Proton, H plus. We want to take off an H plus from something. That is exactly what this is doing. HCl, when it's added to water, it deprotonates, takes off that H plus, and it's left with H plus, and then the remainder, Cl minus. So in other words, if you want to get the TLDR on this, acids, they have hydrogen and they want to lose it. Moving on. Oh, I was there already. All right. So there are different types of acids. We're not going to get into the specific naming of all of them because they're just tough. But some of them have an IC ending. Some of them have a OUS ending. Now, you've heard of hydrochloric acid. That has an ic ending. But we're not really going to focus on the names too much. Some of them are like hydrochloric acid. I'll just tell you the rules, but you don't need to really know them. But for Chem 2, you will be more accustomed to them. All right. If you have a hydrogen ion, so you notice all the acids, one thing about them. They all have this hydrogen in front. hydrogen, hydrogen, hydrogen. Those are all acids. They have hydrogen in front. That is a characteristic thing of acids. So, if you have a hydrogen in front with just an atom, just one element, such as hydrochloric acid, hydrobromic acid, hydroiodic acid, or hydrofluoric acid, this means when it's in this category of just with one element next to the hydrogen, you use this naming. You put hydro in front of it. Hydro, and then it becomes the chlorine, take off the INE, put IC. Hydrochloric, and then acid. That's just the rules of how you name it. This would be hydrobromic, hydroiodic, hydrofluoric. All right. Next is a lot of the times, and most of the time, you're going to have polyatomic ions. They're back. Polyatomic ions bound to this hydrogen. So a common example is H2SO4. What that means is SO4 is sulfate, and the H2 means it's acidic. So this works out charge-wise because you have two hydrogens. Each one of them is +1, so 2 times +1. And then SO4, sulfate, if you recall, the charge of sulfate is -2. +2 and a -2 will cancel out. So that's good. Now, this is a strong acid. And the way you name it would be sulfuric acid. Reason? This sulfate, the 8 ending, turns into an IC. So this is chlorate, turns into chloric. Sulfate turns into sulfuric. That's close enough, but it turns into sulfuric. And you don't say hydro. You don't say hydrochloric acid, because that's what we know hydrochloric acid is over here. This is just chloric acid. That's because it has this polyatomic ion of chlorate. So the rules do get kind of complicated, which is why I'm not going to test you on them at the final, but it is good that we have exposure to it. Another example is you might have some polyatomic ions with the ITE ending, such as chlorite, nitrite, sulfite. So let's do a sulfite example, where this is sulfite, SO4 2-, and it could be H, if you have HSO4, HSO3 2-, or H2, H2SO3, like that. This is called sulfurous acid, because you are taking the ITE ending from sulfite, and you're changing it to OUS. And you add, for sulfur, you add this little UR thing in there just to make it sound better. Sulfite, it would be sulfus acid, but it's sulfurous acid. Sounds better. So those are just some of the rules. But like I said, I'm not going to really test you on those. All right, here are some common acids that come from, and you can see their original names of the anion. So we talked about these singular atom ones, singular atomic anions, where you have chlorine, bromine, iodine, fluorine's another one. Also, cyanide, for some reason, is an exception and falls into that category. So cyanide is a polyatomic ion, Cn-, but once you put it into an acid and make it HCN, it becomes hydrocyanic acid. So it follows this name group, but it's a polyatomic ion. Then you have all of these which have the ATE ending, nitrate, sulfate, carbonate, acetate, phosphate, chlorate, things like that. They go to an IC ending. And then everything, and then acid at the end. Then everything with the ITE, nitrite, sulfite, phosphite, chlorite, those have the OUS ending and then acid. So it's a good thing to be familiar with, know that these rules exist. And you'll have this lecture forever because of YouTube. So that's good. All right, so let's do some examples. Select the correct name for each of the following acids. So you can pause it. So HBr, so we know it's not going to be bromic acid, right? This is a singular atom. That means if you have an H next to it and you make it an acid, it's going to be hydrobromic acid. So that would be C. CO3 is carbonate. Carbonate, let's look back at our rules. The ATE turns into IC. So it would be carbonic acid. BrO2, I think that's bromite. So BrO2 is bromite. the ITE endings turn into OUS acid. So that means it's going to be bromous acid. Let's see if we're right. Yay, we are. Awesome. Good. Let's move on to bases now. All right. So let's write on the top again. So a couple things. We know that acids have H and they want to lose H. Bases have the opposite of H. And you can think, oh, what the hell is the opposite of H? But in chemistry, the opposite, or more specifically, aqueous chemistry, the opposite of H is OH, otherwise known as the polyatomic ion hydroxide. When you have hydroxide in a molecule, it makes the molecule more basic. All right, and there's things that are common for basic: bitter, chalky, and really any soap. Soaps are very basic. They have like calcium hydroxide, stuff like that. They're also electrolytes, and they produce the OH in water. So bases, they produce the opposite. They have OHs, and they want to get rid of their OHs. Just like you see here, NaOH, which is a very common strong base, sodium hydroxide, reacting with water, it splits apart or completely dissociates into its ions of Na plus and OH minus. So it gets rid of that hydroxide ion. That's what's characteristic of a base. It has the OH and it produces it in solution. Sometimes a base might not have OH, but it still produces it in solution. We'll talk about that in the next slide or two when we talk about weak bases, and that one would be ammonia. Great example. But okay, so a base, it has has OH, and then it wants to lose OH. Most important thing for bases is it loses the OH, because sometimes it might not even have OH, but loses OH is important. But most of the time it does have OH. Okay. So naming them, it's very simple. Acids, there's just different rules of naming that we just saw, but naming the bases, I do expect you to be familiar with, because it is exactly the same rules as what we learned with naming simple ionic compounds, because these bases are ionic, a lot of them. NaOH, sodium hydroxide. You say the name of the metal first, then you say the name of the polyatomic ion hydroxide. Potassium hydroxide, barium hydroxide, aluminum hydroxide. So, yeah. So even if there's two or three hydroxides, it's the same name, just like we do for ionic. We never put a prefix, remember that? And we always just name it with the metal first and then the non-metal anion, or in this case, polyatomic anion, and then that name. Okay. So here is the characteristics broken down. The most important thing is that acids, they produce or they release, or in the products, there's H+. Very important. In the bases, the products side of the equation is OH-. They're both electrolytes, and they have different things. They're feeling, honestly, you see like acids sting, yeah, obviously, but really strong bases sting too. But weak bases we deal with, they're soapy, like detergents, stuff like that. Like, also like, why am I drawing a blank? Baking soda. Baking soda is a very common weak base. Litmus paper, all that means is you didn't use it in the lab, but maybe you saw pictures of it when you did the labs. I'm not sure exactly how you're doing the labs, but there's a way to tell how acidic or basic something is by using this pH-sensitive litmus paper, which it changes color based on the acidity or the hydrogen ion concentration. If it's low hydrogen, that means it's pretty basic. If it's high hydrogen, that means it is acidic. And you know that because H+, if there's H+, that means it's acidic, right? If there's no H+, that means it's more basic. Okay, and we'll talk about more of that later. And then phenolphthalein is an indicator in buffers, neutralization. They neutralize each other, which we'll talk about. Okay, so let's try to get through this naming. And in a matching like this, it should be pretty easy. All right, so HNO2. Now, NO2 is, even if you don't know the answer and you look at the answer choices, maybe nitrate, something with nitrous something, right? And there's only one answer, nitrous acid. So that's the answer. And the reason why is because NO2 is nitrite, not nitrate. NO3 is nitrate. So NO2 is nitrite, and then you change the ITE to an OUS and add the acid name on the end, and you get nitrous acid. CaOH2, so calcium, we know that happens first, and an OH, we know it's a base. That's good. But more importantly for the name, calcium hydroxide. H2SO4, we talked about this one as sulfuric acid. And we know it's an acid because it has the H in the front. HIO3, IO3 is iodate. So HIO3 would be iodic acid because the 8 turns into an IC, an ic. NaOH, sodium hydroxide because it's there. I'm getting lazy. All right, cool, good. All right, so another way you can describe acids and bases is by this Bronsted-Lowry theory. Basically, a different group of scientists who came up with a different explanation for how bases and acids work. So before, for Arrhenius, we thought acids have H and they want to get rid of it. Bases have OH and they want to get rid of it. Bronsted-Lowry came along and was like, if that's the case, where are they giving their H's and OH's respectively? If they're releasing them or donating them or giving them to the solution and having them freely floating in solution, where are they going? So they came up with an idea of, all right, let's write an accurate chemical equation for the behavior of acids and bases in solution that is more accurate than Arrhenius. Arrhenius was totally right. I didn't feed you. I hate when professors do that. They tell you the wrong thing first, and then you're paying attention, and they tell you what's right, and you don't pay attention. What I said so far is completely correct, but a more comprehensive way of looking at it was created by Bronsted-Lowry, and this is it: is that an acid is a substance that donates a hydrogen. Donates is a very similar term to releases it or produces it, but it donates it to another substance, whatever it reacts with. A base, on the other hand, is a substance that accepts the hydrogen that the acid donates. So what they're saying is that in every reaction, such as this one right here, even though you see water is in the reaction, there is an acid and a base in this reaction. Right? Even though you see hydrogen chloride, hydrochloric acid, and water, you think, all right, water is neutral. HCl is acidic. So that's what's going on. No. Water will actually act as the base in this case because according to the Bronsted-Lowry, an acid is a substance that donates a hydrogen. So the hydrochloric acid has to donate the hydrogen somewhere. So it takes the hydrogen, it goes away from the chlorine, and it goes to the water. And it creates a hydronium ion, H3+. Just know that it does that. So H3+ is one of the ways it forms in solution, is very similar. It's almost equal to H+, plus water, plus a neutral water. So in solution, these are identical. You can't detect the differences between these. Same thing. Well, in other methods you can, but not worried about this class. Okay, so basically what we're trying to say now is that in every equation there's an acid and a base. And you're like, what the hell? Well, that's neutralization. That's how that works. So what we're going to learn in the next couple of slides is how to identify an acid and a base in a reaction. So if you look at this equation, it's pretty easy because HCl we know is an acid, so by default, water must act as a base. And it does because it accepts a H+. It accepts the H+ from the acid, which loses it. And you get the hydronium ion plus whatever is remaining from the original acid, Cl-. That's how that works. Next, a Bronsted-Lowry base. So if we know an acid is a hydrogen donor and a base is a hydrogen acceptor, another way to think about it is that, well, it's really, never mind, same thing. There's only one explanation, same thing. So Bronsted-Lowry, they didn't really talk about OHs, but you see that it happens anyway. So Arrhenius was correct. But Bronsted-Lowry, as you can see from both of these definitions, if you want to pause here and pause here, they both talk about hydrogen plus only. They don't talk about OH because they thought it was too complicated. And it is. Because for this example, I know I'm going fast, but like I always say, you can rewind it or slow it down. In this example, and I used this example before, I said ammonia. Ammonia is a base, but it doesn't have OH. It just has hydrogen. So you might think, oh, it's an acid. It's got hydrogens in it. Not necessarily. If it reacts with water, what's going to happen is water will act as an acid, and ammonia will act as a base. What happens is water acts as the acid. I have hydrogen, want to get rid of it. Oh, ammonia is like, oh, I'm a base. I like to accept protons. I'm a proton acceptor, hydrogen ion acceptor. So I'm going to take that and become ammonium. Meanwhile, you become hydroxide. The water becomes hydroxide. Now, let's get back to our Arrhenius definition. Arrhenius definition says that if a base produces hydroxide ions in water. Look what this equation just did. Ammonia, when reacted with water, produced a hydrogen ion, a hydroxide ion. So Arrhenius is still right, but here's just a different way of looking at it. So the OH is a byproduct of in a base reaction. A base is going to create an OH ion, and it's going to accept a hydrogen from the water. If a base is just reacting, if you pour a base in water, that is what's actually happening. Okay, let's move on. So in each of the following equations, identify the Bronsted-Lowry acid and base. All right, so let's do that. You can pause and try it on your own, but let's just go ahead and do it. So HNO3, that's an acid. That's nitric acid. It has an H in front, and it's one of the common acids. That means this is the base. So water acts as the base. I don't even have to look at the right side of the equation to know that. And you can even see this acts as a H acceptor, right? The water started out as H2O, went to H3O+, means it accepted the hydrogen. And on the other hand, the NO3 minus acted as an acid, or the HNO3 acted as an acid and lost. So H donator, donate. H donor. Okay, next one. HF. That's hydrofluoric acid, so we know it's an acid. It's got the H in the front, and you can see what happens. It loses the H. So H donor. The water is going to be the base. H acceptor. Okay, good. So I hope that makes sense. Okay. Oh, whatever. We know that. Okay. So a base, I'll say one more thing about bases and we can continue. So a base we know as it produces / loses OH minus, right? This is the opposite of H. So hydrogen, so an acid has the hydrogen, gets rid of it. The base has the OH, gets rid of it. But since acids and bases are opposites, the other way you could think about it is it gains H plus that acid loses. So it gains the H that the acid lost. Okay, so the next thing we're going to learn is conjugate acid-base pairs. What this means is that we've kind of already learned this. Now, if you take the previous equations, let's look at A, this one. If you look at the pair of the acid before the reaction happened and then afterwards, so let's take the NO3 and the HNO3. What this is called is a conjugate acid-base pair. The acid is here. The acid's conjugate base is here. So conjugate base. And I know this terminology is tough. It might be difficult. I'll try to explain it. And if you have any questions, let me know. But I'm not going to go crazy with this on the exam, on the final. So this is an acid. An acid has a conjugate base. And what that means is once the acid is conjugated, or meaning dissociated, once the hydrogen comes off, whatever's left over is the conjugate base. Meaning if the reaction went in reverse, let's say we look at it backwards, the NO3 would end up gaining a hydrogen if it went backwards. Meaning if it gains a hydrogen, it's a base. So by that metric, you can say that HNO3 and NO3 minus is a conjugate acid-base pair. So the next part is we're going to be able to identify these conjugate acid-base pairs by looking at the equation and seeing what's similar. And here in water, we have this is the base. This is the base's conjugate acid. Conjugate acid. And what that means is, since the base, water, accepted a hydrogen and became an acid, if the equation went the other way, it would lose the hydrogen and therefore act as an acid. So it can just go back and forth. In this case, you can really see it go back and forth. Now, okay, so I hope that makes sense. A good question would be oh, professor, how come there's only one line here and two lines here? That is because of equilibrium, like we learned in chapter 10. This HNO3, nitric acid, is a strong acid and will only 100% dissociate and will not go backwards. HF is a weak acid, hydrofluoric acid, and it can go back and forth, and it goes back and forth, the forward and reverse reaction, until equilibrium is reached. So that is why. And another good question would be, oh, professor, what is the difference between a strong acid and a strong base, and how do you know which one's which? Well, I'll tell you soon. So we understand this already. We understand the pairs. All right. So let's do this. Write the conjugate acid base, conjugate base for each of the following acids. So you can do it on your own. You can pause it, but it's not that hard. So if you imagine this reacting, it's for an acid. These are all acids, right? They start out with the H, and they want to lose the H. So once they do, it would be Br minus. This one loses an H, HS minus. This one loses an H, HCO3 minus. And you notice for B and C, I didn't remove both hydrogens. You're supposed to only remove one hydrogen at a time. For some acids, like these two, B and C, what is that even called? I think it's hydrosulfuric acid. Yeah. Hydrosulfuric acid, something like that. There are actually two. It's called it's called a diprotic acid, meaning it has two protons and there's two different dissociation steps. Each one of them has their different rate of dissociation. And that's where Chem 2 you really get into that. And there's actually little calculations you can do with that to figure out the pH of certain solutions that are that have multiple protons to be removed. So there could be multiple protonation steps. That's actually some fun math. It's like a system of equations. But if those of you who don't like math, sorry about that. But I won't teach you that. Okay, so it's not in the curriculum. So write the conjugate acid for each of the following bases. So we're going the opposite way. So these are bases, right? They're conjugate bases for the following bases. So we're going to add the H. That's what bases like. HNO2, NH4 plus, HOH. Ding, ding, ding. What's HOH? Oh my God, it's water. H2O. That's crazy, right? Now we just stumbled upon something very interesting. If someone ever asks you, oh, you took chemistry, you must know a lot. Why is water neutral? You'd be like this. Well, water is composed of two of the opposite acid and base components. It's produced by adding a hydrogen plus, which is characteristic of an acid like we just learned, and OH minus, which is characteristic of a base that we just learned. If you add them together, you get H2O, which is, by definition, pH of 7 or 100% neutral, and does not lean towards any side, the acidic side or the basic side. So that is why water is neutral. It's composed of both acid and base elements in equal parts. All right, so we did that. Good. Identify the sets that contain acid-base conjugate pairs. So we want to, in this kind of question, we're looking for which pairs have just the difference of a hydrogen removed or added. One hydrogen. So the first one, HNO2, NO2 minus. Yep. Second one, H2CO3, CO3 2 minus. Nope, because both protons are removed. HCl, ClO4 minus. Nope, they're completely different. HS minus, H2S. Yes, they only differ by one hydrogen, so the H2S is a acid, and the HS minus is its conjugate base. Very important terminology for later on. NH3 is ammonia. NH4 plus, they are conjugate acid-base pairs. NH3 is the base. NH4 plus is the base's conjugate acid. And I'll say those terms for one as well. HNO3 is the acid. Sorry, HNO2 is the acid. NO2 minus is the acid's conjugate base. When this acid becomes a base or loses the hydrogen, it becomes NO2 minus. So I hope that makes sense. All right, good, good, good. All right. Identify the conjugate acid-base pairs in the following reaction. Okay, so this could be a little bit daunting because if you try this on your own without being pushed along, it might get difficult if you just see an equation and you're asked a certain question. But the first thing I would like you to do is find the acid on the reactant side. Find something with an H, something that you know is the acid, and from there, you can deduce all of the information. So let's do that right now. Let's look at the first thing, HNO3. Totally the acid, definitely. That means, by definition, the other thing, even if you don't know what it is, must be the base. The acid has an NO3 in it. Once the H is removed, and it becomes NO3 minus, this is the conjugate base. And you can do that. Then once you have NH3, ammonia, and you add or you accept the proton that is taken from HNO3, you get NH4 plus, which is the base's conjugate acid. Like that. All right, good. Okay, so let's move on. Good, good, good. All right. Strengths of acid and bases. All right, we're going to skip this whole thing, and here's what we're going to do. I'm going to go, and this is what you can do. You can either memorize this, which is, oh, these are all the strong acids and weak acids and strong bases. I have a genius way of telling you, and we already know about strong and weak dissociation. We went over it in electrolytes. It's the same thing. So right here, I'm going to add a slide. Okay. So this is a trick that is not in any textbook, and no teacher will teach it to you because me and my friends made it up in college. To memorize every single strong acid and strong base and weak acid and weak base, there is a very simple mnemonic to know. And I'm going to write the mnemonic down and I'm going to say it, but luckily we're on YouTube and you can repeat it multiple times. So it goes Hickel, Hibber, High, Hino, Hicklow. There's actually two Hicklows. It's not foolproof, but it's pretty good. Hisso. So these are strong acids. Weak acids. Everything else. Everything else not on list. Strong bases. There's no mnemonic for strong bases. It's just group 1A/2A hydroxides, and then weak bases. Everything else not on list. Okay, so let's go through this. If you want to be a complete baller going into Chem 2, you need to memorize, you have all the strong acids memorized, and your professor asks you, oh, who knows if hydrochloric acid, or sorry, that's an easy one, chloric acid is a strong acid or not. And everyone's like, oh, what do I do? And you're like, oh, Hickel, Hibber, High, Hinoa, Cloiso. It's one of them. Therefore, strong acid. You will be like, you get an A automatically. Well, probably not. Yeah, I don't know. Depends what you have. But the strong acids, the mnemonic, is Hickel, Hibber, High, Hino, Hiclo, Hiso. Hickel, HCl. Hibber, HBr. High, HI. Hino, HNO3. Hiclo, HClO3 and HClO4. They're very similar in strength. Then Hiso, H2SO4, which is the strongest of the strong acids. Hiso, sulfuric acid. If it is an acid and it is not on the list, it is a weak acid. Oh, professor, that's it? Aren't there strong acids not on the list? There are, but they're not common in chemistry, and they're not for inorganic chemistry or organic chemistry, really. They're for crazy science. There's like other things that are beyond the scope of this class. These are the most common ones that will come up in any chemistry lab, organic chemistry lab, that are strong acids. Just this list. Weak acids is everything else. So, for example, HF. Organic acids, you want to do benzoic acid. That's a common organic acid. So, citric acid, right, in orange juice. Citric acid. All of those are weak acids because, well, the real reason is because they partially dissociate, but because they're not on the list. They're not on the strong acid list. All right, going on to strong bases. The only thing you have to know for strong bases, group 1A and group 2A hydroxides. Things that involve that are NaOH, right? Group 1 is Na. And in group 1, I do not mean hydrogen. I just mean the metals in group 1. So you have, what else? Potassium hydroxide, right? Group 2A, you have calcium hydroxide, magnesium hydroxide, strontium hydroxide, stuff like that. So those are all strong bases. And everything else that is not on the list is a weak base. And there is one weak base that you should be familiar with. And we've seen it twice already. Ammonia is NH3. Ammonia, like that. That's ammonia, NH3. It is the most common weak base in any chemistry problem. Other ones, I'll just write another one. Let's go FeOH2. Iron 2 hydroxide, for example. Right? Because it's a hydroxide, but it is not group 1A, 2A. Iron is somewhere in the middle. So it's a weak base. Okay, so this is the cheat sheet for everything you need to know about strong and weak bases and acids. Good. So there are also other acids that have multiple protons and multiple H's that we saw already. These are called diprotic. There's triprotic, polyprotic acids. And the only thing we need to know for that is, like I said before, they have multiple dissociation steps. The first one of carbonic acid we see right here is H2CO3. Once it reacts with water, it loses one of its H's and becomes HCO3-. This HCO3- is also considered a weak acid because it has a proton that can still be deprotonated. Oh, why can it be deprotonated? Because it's a weak acid and it has one of those K values, one of those equilibrium constant values. So that means the reaction goes to a certain extent, and it deprotonates naturally. So once it reacts with water, it loses its remaining hydrogen and just becomes carbonate ion. Meanwhile, all the water molecules in the solution are protonated, and they become H3O+. Here's another example with sulfuric acid being diprotic, but there are triprotics and polyprotics as well. All right, strong bases, we did this already. We're great at it. Boom, we're good. Strong bases, oh, whoa, instead of memorizing this list, you could just memorize the rules I put before. So, yeah. All right, now let's do these rules. Identify each of the following as a strong or weak acid or base. Oh, it's got an email from one of you guys. Okay, I will respond to it after lecture. All right, so identify each of the following as a strong acid, as a strong or weak acid or base. HBr. Let's think about the song, or the mnemonic. I'll write it down again. So the mnemonic is Hickel, Hibber. Oh shit, Hibber. Sorry, I said a curse. But anyway, Hibber. So that is a strong acid. Hickel, Hibber, high. Hino. Hiclo. Hiso. HNO2. This is where it might get a little bit confusing because HNO3 is strong, but HNO2 is not. So it's got to be on this list. It can't be a conjugate or something. Oh, it's close to something on the list. Oh, it's HClO, so it might. No, not true. It's got to be exactly on this list. So HNO2 is weak. NaOH, it is a group 1 hydroxide, therefore it is strong. H2SO4, it is the strongest of the strong acids. It's over here in our mnemonic. And then copper 2 hydroxide, it is not in group 1A or 2A, being copper, so therefore it is a weak base. See that? Good. All right. So dissociation constants. Now we went over this with equilibrium, and it's very similar. So it's really the same thing. The equilibrium constant, if it's small, meaning less, by small we mean less than 1. If it's small, less than 1, that means the equilibrium lies to the left, and there's more reactants when the reaction's finished. When the reaction reaches equilibrium, the concentration of the reactants is higher. And remember, the equilibrium constant, to calculate it, is, in general, a ratio of the products over the reactants. There's more that goes into it, but it's generally expressed by some kind of ratio between them. There are exponents involved based on the coefficients, blah, 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 but it's a ratio, nonetheless. So if this ratio is small, that means the reactants have a bigger number in the denominator, therefore favoring the reactants. If it's large, that means the products, or the numerator, I was about to say numerator. The numerator is bigger, therefore we have more reactants, and the equilibrium lies to the right. Or sorry, more products, and the equilibrium lies to the right in favor of those products. So, general rule of thumb, weak acids, right? If we're thinking about it in an acid-base perspective, where HCl becomes H plus Cl minus, in a strong acid, all the molecules in this reaction are going to be over here in products. Very few, 0 are going to be here. Like literally 0, maybe 1. Here there's going to be 100,000. Right? If you take or let's say 1, because we can't have a fraction with 0 on the bottom. All right. So say 1, right? This reaction constant, this equilibrium constant, will be products 100,000 over 1. That's huge. So that makes sense. Strong acids have a very large Ka value. And they call it Ka because it means equilibrium constant acid. And they have Kb, meaning equilibrium constant of bases. Now, weak acids will be HF, goes into H plus F minus, H plus F minus, and it will be a double arrow. Since it is a weak acid and only partial dissociation occurs, you're going to have more of the molecules still being reactants. So reactance is going to be high, meaning the bottom number here is going to be high, meaning the top number is going to be low, and you get a small Ka, a lot less than 0. Ka's for weak acids might be 10 to the negative 6th. For strong acids, it might be 10 to the 4th or something like that. So they're very, very big difference. Okay, so yeah, here's how to calculate it. We talked about that already, but we don't need to go in detail. Here's some examples. So here's a bunch of weak acids, and you see how the equilibrium constant is very small, 10 to the negative 3rd, 4th, 5th, all the way down to the 13th. And bases, same thing. For Kb, for weak bases, same thing. Okay, so dissociation of water, we talked about that a bit. Yeah, we don't need to worry about that. Let's just get to the point. The point is with pH. Okay. Wait, so we get that. All right, so the pH scale, yeah. Here we are. Okay, so what pH is. So the reason why I skipped all that is because it kind of preludes to this one slide, which I'll just tell you, I'll cut to the chase. Because it gets really mathy. It's kind of like, oh, this is the proof that pH works. I'll just cut to the chase. Basically, the pH is a scale that's used to determine acidity. And the scale calculation is based on the concentration of hydrogen ions in the solution. So if you have more hydrogen ions in solution, that equals lower pH equals more acidic. So more hydrogen means more acid, lower pH. If you have a low hydrogen ion concentration in the solution, you're going to have a higher pH. And we'll see how the equation works. Higher pH equals more basic. So let's figure out how this works. All right. So this, ignore this part. It goes from 0 to 14, but actually can go negative or over 14. So this is the most important part. Pretty good circle. Oval. Acidic solutions have a pH lower than 7. Neutral solutions have a pH of 7 exactly. If it is 7.001, it is basic. If it is 6.998, it is acidic. But not many instruments can tell the difference between those two. Not the point. Point is, the only way for it to be neutral is pH of 7.0 exactly. And water is the universal neutral thing. If there's no ions in the water, it is 7. Basic solutions are above 7. Okay, so there are different ways to determine pH. One of those is litmus paper, like I said over here in B. Over here, which changes color based on different types of acids and different acid strengths, and there's a pH chart that it has. There is a pH meter, electronic pH meter, which actually has a hydrogen ion selective electrode, which it basically reacts and detects and creates a voltage based on the amount of hydrogen ions in the solution, and that voltage is translated into a signal, and that signal is translated into a number based on the intensity of it, which can be converted into a pH. And we, in my lab, we use this because it's the most sensitive. We don't have to keep using papers. We don't want to dip our papers in our protein solutions or do anything, so we use this. This one is the indicators. So an indicator is another way. There are certain chemicals that once you put a few drops, phenolphthalein is one of them. There are a lot of different indicators, but when you put certain drops into a solution, if it, let's say it starts out blue like this, if you drop them into a solution and it turns red or turns a different color, it actually changes color based on pH. And the reason why is because these solutions naturally fluoresce, and they fluoresce differently when they're in contact or bound to different molecules, whether there's more acidic molecules or more basic molecules in the solution. they react differently, and they create a color signal that can be visually detected or detected with absorbance. But that's into another class. Okay. So here's the pH scale of common things that we find. So let's start out at really acidic. The most acidic thing you can think of, well, it's actually pH that's negative, but let's just say a 1 molar concentration of HCl in a solution. That's pretty acidic. Then you have gastric juices. So our stomach has a pH of like 1 or 2, 1.6 according to here. Now, that is really low. That's really acidic. If our stomach juices, our stomach acid, went on our skin, it would burn our skin. So how does that in our body all the time? We're running around and stuff, like it's juggling up and down. That is because of our stomach mucus lining is so tough, and it's adjusted and adapted, and those cells will not die in the presence of pH 1.6. So that's due to evolution, and the different cell types, right? Our skin cells are not the same as our colon cells and our duodenum cells, right? So that's in the digestive system. Now, what was I going to say? I don't know. Yeah, pH. It's pretty acidic in our stomach. Oh, here's what I was going to say. I guarantee you've all felt that stomach acid burn you. And it does. Examples. Vomiting. So if you throw up, it burns. Why does it burn? Those gastric enzymes, that environment, is a pH of 1.6 to 3. That's going to burn your upper lining of your esophagus and inside your mouth. Because your mouth and esophagus are not used to having low pH substances in there. They're used to having food go down and water go down and drinks. Right? So that's where you see. And also people who have acid reflux and heartburn. Right? Heartburn has nothing to do with your heart. It's all the buildup of acid that's secreted by your mucous membranes in your stomach, because there's some kind of unwanted food in there. Let's say you have a bad diet. Let's say you're lactose intolerant, right? Your stomach doesn't know what to do with lactose. Once you get lactose, your stomach's going to create a bunch of enzymes, to try to break it down. It's not going to work. It's going to create more. It's going to secrete a lot of juices that are really acidic, a lot of acid to try to break it down. It's not going to work, or it might work a little bit over time. But what that does is that all that acid will build up, and it'll start to reflux back into your esophagus, and you'll feel like a burning, and you might burp, and you just won't feel comfortable because you ate something that doesn't agree with you. And your stomach is used to a certain diet, and it has a normal amount of acid production. But if you put something, let's say bad meat, if you eat bad meat, your body's going to be working overtime to produce more gastric enzymes and gastric acids to break down that bad meat than it would if it was good meat, because your body is used to that. So that's how your stomach works. Then you have other things: coffee, potato, water, plasma, milk of magnesia, bleach. Don't drink bleach. It does not cure coronavirus. So 1 molar NaOH is very basic as well. Okay, cool. All right. Identify each of the following as acidic, basic, or neutral. HCl, pH of 1.5. Acidic. Pancreatic fluid at the H3O plus concentration. So, another thing. So, this bracket means molarity, right? If you have something in there, that means it's the concentration of whatever's in there equals something. So here is, remember we said before, how H3O plus is equal to H plus? Same thing. This is saying the hydrogen ion concentration is 1 times 10 to the negative 8. Now, I don't think I wrote down here I don't think so. The equation for pH, very important. I don't know why it's not here. All right, here's the equation for pH, and I definitely suggest writing it down. It will be on the exam. pH equals the negative log of the hydrogen ion concentration. Okay, So what that means is if you go in your calculator, I suggest trying this out with these problems right now. So you take your calculator, type in negative. Then you type in log, which is probably a log button on your calculator, and you might get log with a open parenthesis. Then you put in whatever the hydrogen ion concentration is. In this case, 1 times 10 to the negative 8. So I'm not going to put the 1, you put 10 to the negative 8. Close the parenthesis, click enter, and you get 8. And then that's the pH. And the pH of that means if it's 8, it's over 7, meaning it's basic. This is acidic. Okay, so hopefully that makes sense. Other calculators, you might need to write the number in first. So you might want to do 10 to the negative 8. Click the log button. It will give you negative 8. And then you got to negative that. So if you negative that times negative 1, you get positive 8 as your pH. So those are 2 ways to do it on different calculators. Now let's get back to this problem. That's important, knowing that equation. So this is the pH equation up here. pH equation. Oh, I could change colors. I didn't even know that. pH equation. Oh, I like that. Cool. All right. So Sprite soft drink pH 3. Lower than 7, acidic. pH equals 7, neutral. OH, this is where it gets a little bit complicated. OH is 3 times 10 to the negative 10. I gotta do math for that. I don't feel like doing the math. I'm gonna look. So basically what you would do, where's my mouse? There you go. Okay, it's acidic. So basically what you would do is, I'm not going to give you that on a test. Basically, you would know that 10 to the negative 14 is the total that you need to get. So basically, what we know as a fact is the concentration of OH minus times the concentration of H3O plus is equal to 10 to the negative 14. So you put in 3 times 10 to the negative 10 here times H3O plus concentration, or just H plus, and you're supposed to get 10 to the negative 14. You do the math there, you divide, blah, 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 and you get a number. Then from this number, you put it into the pH equation, and you get a pH. I know I'm being lazy there, but I'm not going to test you on that. And then this one, you do the very similar thing, but we can just take the log of that. So H3O plus concentration, if we know the concentration already, we can just put that number into the log formula, and we can get the pH for it. 3 times, I'm going to put that in my calculator right now. Negative 12. Log of it. Oh, I did it wrong. All right, log of it. Time. I'm doing it on my phone. So, negative 12. I got 11. So I need to do the negative log. So it's positive 11.3. That is very basic. This one's acidic. All right, cool. So look, we did good. All right. So the last thing, there's actually a lot more. Damn. Okay, we'll probably skip the last section because it's redundant. All right, where are we? All right, so reactions of acids and bases. Now, the most important one is an acid neutralization. Here we go. So acid neutralization, we already kind of talked about when we went over conjugates. And the same thing's happening. But before with conjugates, we were just adding an acid or a base to water. Now we're adding an acid or a base to the opposite, or to an acid or a base. If we add an acid to a base, what's going to happen? They neutralize each other, and they create a salt and water. That is always a thing, very important. So I'm going to circle that. So an acid and base react to produce salt and water. It's not always going to be NaCl, but it's always going to be water. So what happens here is the acid is going to donate the hydrogen to the base. The base is going to get rid, or it's going to donate it. The OH is going to be donated as well. Or, I don't like the arrows. Oh, I could do that. Wow, I have a button for that. Cool. So, in solution, the H plus is going to be removed. The OH is going to be removed, right? Because bases produce OH in solution. Acids produce H in solution. These OHs and H's, positive and negative, are going to meet each other and create water. And the remainder, Na plus and Cl minus, will create salt. Very simple. That is acid-base neutralization in a nutshell. So let's do one on our own. So write the balanced equation for the neutralization of solid magnesium hydroxide and nitric acid. All right. So I'm going to take this, copy it, and then we will go to a new slide and do this on our own. All right. So write the balanced equation for magnesium hydroxide, MgOH2. And think about it. Is it a strong or a weak acid or base? It's in group 2, magnesium, so therefore it is a strong base, and it has OH. Magnesium hydroxide plus nitric acid. So nitric acid is HNO3, and it is a strong acid because it's Hickel, Hibber, High, Hino, right? It's part of that list. All right, so what's going to happen here? The OH is going to be removed. The H is going to be removed. And you're going to end up with MgNO3, 2, because Mg is 2 plus, NO3 is 1 minus, needs to be 2 of them, plus H2O, water. So that's what's going to happen. Now, you could be thinking, oh, there was 2 OHs here. Where'd they both go? They both left, but the equation isn't balanced yet, so we'll do that right now. That's why it says write a balanced equation. Mg, there's one of them here, good. OH, there's 2, there's 1. Now, whenever we're balancing acid and base reactions, always write water as HOH. So I'm going to do that right now. So water, write it as HOH. It just makes your life easier. OH, there's 2. OH, there's 1. So that means we put a 2 here. H, there's 1. H, there's 2. 2 here. 2, NO3. NO3, 2. Done. So that's good. So yeah, that's basically how it works. Yeah, not really much else than that. We did that. Good. Okay, let's do this one. So write a balanced equation, magnesium hydroxide and HBr. So we'll do that right now. So we know that it's an acid-base neutralization, and we're going to have the OHs are going to be removed. The H's are going to be removed to create water. Or, sorry, we'll do HOH. Just to get you guys in the habit of that. We'll write it in a different color. We'll do HOH plus whatever's left over, which is the anion Mg, and then the cation Mg and the anion Br2. So let's balance this. Mg, there's 1. I'll balance a different color. There we go. Mg is 1. Mg, there's 1. OH2, there's 2. OH, there's 1. So we're going to put 2. HBr, there's 1 H here, 2 H's here. Put a 2. 2 H's, 2 Brs. Br2. Awesome. Done. Okay. Did that. Alright, we can balance these. We'll do the first one. So let's do this real quick. We'll do it in green. Alright, HCl. So just for practice, let's write this water as HOH. So we have 1H, 1H. We're good. 1Cl, 3 Cls. Uh-oh. Put a 3 there. Now we're going to go back. 3H, 1H. Put a 3 here. 3Cl, 3Cl. Good. Next. Al, 1Al, 1Al. OH, 3. 3 OH. Good. So the coefficients would be 3, 1, 1, 3. So it would look like this. And let's just do this one for comprehension. So, or to be comprehensive. BA, there's 1. BA, there's 3. 3 there. OH, there is 2 times 3. Now there's 6. OH, right, HOH. OH is 1, so we'll put a 6 here. Then, we can see the answers between B and C. So then we'll go to H3PO4. There's 3 here. There is 6 here. So we're going to put a 2 here. 2H3 means that there's 6 H's. 6 H's here. 2PO4. PO4, 2. Done. Hopefully you understood just my ranting just now of how I balance these equations, but that's my thought process when I balance them. And you need to know balancing for the exam. So I'm just going from element or ion to ion and just balancing away as I go along. And it's good to split the water into HOH when we're doing these types of reactions. Good, we got it. Awesome. Good. Okay, so you covered this in your lab a little bit, I think. So, but we are going to talk about it a little bit. Now, the antacids. We're not going to talk about the experiment. We're just talk about antacids real quick. So, remember I just mentioned how you get excess stomach acid in the event that you eat something that doesn't agree with you, or maybe you're just prone to excess stomach acid. The way you relieve this is by antacids. These antacids, they're common right here. You have Rolaids, Tums, and stuff like that. They are weak bases, right? So strong bases, you may think, oh, acids are bad, bases are good. No. If you have strong acids or bases, they're both really toxic and going to hurt you. If you have weak stuff, like citric acid is good for us, ascorbic acid is vitamin C, and it cures almost everything. So it's an acid. Then you have antacids, which are very weak bases, such as aluminum hydroxide, magnesium hydroxide, iron hydroxide, calcium chloride. Actually, is even though it doesn't have a hydroxide, it's still considered a very weak base. Or sorry, calcium carbonate. My bad. Calcium carbonate. It's still considered a pretty weak base, and it's a bunch of mixtures. So here's a bunch of different antacids, and they have different efficacy, but most of them are pretty similar in terms of ingredients. And you see calcium carbonate for Rolaids and Tums, Pepto-Bismol. So that's, even though it doesn't have the components of a normal base like we just learned, it's still considered to be a base. A weak one, very weak one. Okay, last thing we'll cover. We're not going to cover buffers. Last thing because we already did the concept. So acid-base titration is basically is a common chemical technique, titration in general. What that means is you have a known volume or molarity of a substance, and you want to figure out the molarity of another substance that's unknown. And we do this in chemistry and even in biology a lot, because there's a lot of unknowns. Like me and my colleagues and whoever for our research, it's all like front lines, or what do we call it? The cutting edge of science, because it's very unexplored territories in what we're doing. We can't go online and look up, oh, how did this experiment go for this one person? A lot of the times we're doing it the first time out of anybody. So we have to know what concentrations of certain things are when we don't know them. So we do titrations. For acids and bases, you can add a known amount of a base to an acid, drop in an indicator, and that indicator will change color, as seen in the third picture. It will change color when the neutralization point is reached. That's how you know how much acid there was originally in that solution. Because once it's neutralized, you can backtrack. You can calculate and be like, wait, I added 25 milliliters of NaOH to neutralize it because it changed to pink. That means there must have been the same concentration, or let's say if there was 50 milliliters in here, that means it must have been half the concentration of the stuff that I put in. So it must have been not 1 molar, but 0.5 molar if it took half as much to neutralize it. Stuff like that. And that equation actually is the dilution equation. But we're not going to use that to solve these problems. But that's just how it works. You're going to use a known amount of either base or an acid to figure out an unknown concentration of a base or an acid by a neutralization reaction that is determined by this indicator solution. So before you start in this first picture, you drop maybe 2 or 3 drops of an indicator. When you do that, nothing will happen. Then you keep adding, and you'll see a little bit of a pink color, and then you swirl it, it'll go away. And you keep adding and adding and adding drop-wise, and then eventually that pink color won't go away. That's when you reach the acid-base neutralization point, or the end point of titration. They call it the end point of titration. So, yep, that's how that works. That's the titration. Okay. So here's how that works. Yeah, indicator. So you use phenolphthalein is a common indicator that changes color around pH 7 when the solution is completely neutralized. So, yeah. Yep, buffers basically. So we'll talk about buffers for a little bit. So basically, buffers is a chemical system that is resistant to the change in pH. And what that means is it has both components of weak acids and its basic counterpart. So a good buffer system, I'm going to write this down. So a good buffer has a weak acid plus its conjugate base or vice versa. Oh, my cat wants to play fetch. She brought a ball. That's nice. We're almost done. Okay. So it's a weak acid and a conjugate base, or a weak base and a conjugate acid. The reason why is because if you take a buffer solution that has this and you add an acid to it, the acid will be automatically neutralized by the base. If you add a base, it'll be neutralized by the acid. This can happen only for so much of stuff that's added, but the idea is that for a certain period of time, otherwise known as the buffer capacity, the solution resists the change of pH and may change a little bit. Whereas if you look up here for water, pure water, pH of 7, you add an acid or a base, the pH will drastically change. But if you have a buffer system, a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid, only a small amount of change in the pH will occur. But if you keep adding and adding and adding, it will get larger change. But the idea is that it resists pH change because it is a combination of acids and bases that can neutralize a component that's added, an acid, acidic or basic. It could either neutralize acidic or basic. It could do both, is what I'm trying to say. It could do both acidic or basic neutralization. That's why it's considered a buffer. We have buffers in our blood that maintain our pH around 7.4. So yeah, buffer solution contains a combination of acid-base conjugate pairs, a weak acid and a salt of its conjugate base, such as these. So this is a weak acid, is acetic acid, and its conjugate base. So it could also be a salt of its conjugate base. So what that means is if you have HC2H3O2, and then you have, let's say, sodium acetate, that would work. Because this salt, sodium acetate, will break apart into Na plus and acetate minus anyway. So it'll basically be the conjugate base of acetic acid. Yeah. Okay. So that's about it. We're not going to really cover the rest. It's just like buffers in our blood, whatever. I'm not going to test you on that. So, videos on the back in the last slide, acids and bases, pH scale. I will be posting a video about the end of chapter 10 because I did a really sloppy explanation on that. I just want to go over gas-chemical equilibrium. I found a better way to explain it, so I'm going to do a short video probably tomorrow on that. I'm really tired. It's almost 1 a.m. I'm doing this. My roommate's going to kill me. Anyway, so that's it. Enjoy your week. Stay safe. Everybody working in healthcare, please stay safe. and flatten the curve. And just to show you Blackboard one more time, our final exam is until May 22nd, midnight, and it will cover chapters 2 through 11. And I will be posting more lectures for additional material that is good for Chem 2 and beyond, and just general knowledge. So enjoy your weeks. Let me know if you have any questions, and have a good night or day.